4 light-years away, something massive is hiding in our nearest stellar neighbor, and it keeps disappearing. The James Webb Space Telescope just revealed discoveries that are rewriting everything we thought we knew about the universe around us. Black holes that grew too fast, planets that should not exist, and worlds so close to Earth we could almost reach them in a human lifetime. We are about to journey from dying stars on the edge of explosion to frozen planets wandering alone through the void. If you enjoy this, a like and subscribe helps more than you know. Now take a breath. We begin. Four light years. That is all that separates us from Alpha Centauri, the nearest star system to Earth. If you could travel at the speed of light, you would arrive in less time than it takes to finish college. In cosmic terms, this is our backyard, our neighbor, and in August of 2024, the James Webb Space Telescope pointed its golden mirrors at this system and found something no one expected. A planet, a gas giant roughly the mass of Saturn, orbiting Alpha Centauri A at about twice the distance Earth sits from its own star. This places it squarely in what scientists call the habitable zone, the region where conditions might allow liquid water to exist. Now, a gas giant itself cannot support life as we know it, but moons around such a world could. Think of the fictional moon Pandora from the film Avatar. That story was set in this exact star system. And now, reality may be catching up to fiction. But here is where things get strange. When astronomers looked again in February of 2025, the planet was gone. They searched again in April. Still nothing. The world had vanished. Scientists ran millions of computer simulations to explain this disappearance, and they found an answer that sent chills through the research community. The planet had not vanished. It had simply moved. Its orbit is not circular like Earth's. It is stretched and elongated. Sometimes the planet swings close to its star, too close for Webb to see against the glare. Other times it drifts farther out, becoming visible once more. This means the planet is real, confirmed by multiple observations and backed by years of data from ground telescopes dating back to 2019. If verified, this would be the closest exoplanet ever directly imaged, the nearest alien world we have ever seen with our own instruments. And it exists in a place we could theoretically reach within a single century using technology that is currently being developed. But the discovery raises uncomfortable questions. Alpha Centauri is a binary system, two massive stars locked in a gravitational dance, orbiting each other every 80 years. For a planet to survive in such a chaotic environment seems almost impossible. The gravitational forces should have torn it apart or flung it into the void long ago. Yet there it is, or there it was, waiting for us to look again. The research team is already planning more observations. They believe the planet will reappear when its orbit carries it back into view. The Nancy Grace Roman Space Telescope, launching in 2027, may finally confirm what Webb has hinted at. A world next door, hiding in plain sight, dancing on the edge of visibility. And if one planet can survive in such a violent system, what else might be lurking in the spaces between those twin stars? The answer may arrive sooner than we think. But before we look outward, we need to look closer, because Webb also turned its gaze towards something heading directly at us. On December 27th, 2024, astronomers discovered a rock tumbling through space. They named it 2024 YR4, and within weeks, it had the attention of every space agency on Earth. The asteroid measured somewhere between 130 and 300 feet across, about the size of a 15-story building. That might sound small compared to the dinosaur killer that struck 66 million years ago. But an object this size hitting a populated area would release energy equivalent to several nuclear bombs. It would flatten a city, incinerate everything within miles, and send shockwaves across an entire region. The problem was its trajectory. Early calculations showed a small but measurable chance that this asteroid would strike Earth on December 22nd, 2032. The odds started low, then they climbed. At one point, the probability of impact reached nearly 3%. That may not sound like much, but in planetary defense terms, 3% is terrifying. NASA made a decision that reveals just how seriously they took the threat. They pointed the James Webb Space Telescope at the asteroid. This is extraordinary. Webb was designed to peer into the distant universe, to study galaxies billions of light years away. Its time is precious and carefully scheduled years in advance. Yet they redirected it to track a tumbling rock in our own cosmic neighborhood. Why? Because Webb sees in infrared. It detects heat, and that heat allows scientists to measure an asteroid's true size in ways that visible light cannot. When an asteroid reflects light from our star, its brightness depends on two factors: size and surface reflectivity. A small, shiny asteroid can look identical to a large, dark one. This uncertainty plagued the early estimates. Was this rock 130 feet across and highly reflective, or 300 feet across and covered in dark material? The difference matters enormously when calculating potential damage. Webb's observations in March of 2025 delivered answers. The asteroid is roughly 160 feet wide, still large enough to cause regional devastation, but smaller than the worst-case scenarios predicted. More importantly, continued tracking refined its orbit. By late February, NASA announced that the risk of impact had dropped to near zero. The rock will miss us, confirmed, but the episode exposed something uncomfortable. We almost missed it entirely. The asteroid was discovered less than 8 years before its potential impact date. If the trajectory had been slightly different, if the odds had been higher, 8 years might not have been enough time to mount a deflection mission. And here is what keeps planetary defense experts awake at night. There are millions of asteroids in orbits that cross Earth's path. We have catalogued only a fraction of them. The next one might not give us 8 years of warning. It might give us 8 months or 8 days. Webb proved it can help, but Webb cannot watch the entire sky. Something else is out there, something we have not found yet. And while we worry about rocks falling from above, the telescope revealed something far more disturbing happening to worlds we once believed might harbor life. 40 light-years from Earth, a small red star burns with a dim, steady glow. Around it orbit 7 worlds, all roughly the size of our planet, all made of rock. When astronomers discovered this system in 2017, it ignited imaginations around the globe. The TRAPPIST-1 system, 7 Earth-sized planets, 3 of them sitting in the habitable zone where liquid water could exist. For the first time, humanity had found a place that looked like it might, just might, hold the conditions for life. Then Webb took a closer look, and the dream began to crumble. The innermost planet, TRAPPIST-1b, was the first to fall. Webb measured its temperature by watching it pass behind its star and reappear on the other side. The readings showed a scorched surface with no atmosphere to speak of, just bare rock baking under relentless radiation. TRAPPIST-1c came next. Same result. No thick atmosphere. No protective blanket of gases. Another dead world. Then came the crushing blow. TRAPPIST-1d sits right on the edge of the habitable zone. Scientists had pinned enormous hopes on this world. It receives about the same amount of energy that Earth receives from its own star. If any planet in this system could support liquid water, this was the one. In August of 2025, researchers published their findings. Webb's instruments searched for water vapor, methane, carbon dioxide, the molecules that make up breathable atmospheres. They found nothing, no signatures, no hints. The data pointed to one of 3 possibilities. Either the planet has an atmosphere so thin it resembles Mars, or it is wrapped in clouds so thick they block all detection, or it is simply a barren rock with no atmosphere at all. The lead scientist put it bluntly, "We can rule out TRAPPIST-1d from the list of potential Earth twins." Confirmed. Another hope extinguished. The culprit is the star itself. Red dwarfs like TRAPPIST-1 are volatile and violent. They unleash flares of radiation that dwarf anything our own star produces. These flares bombard nearby planets with enough energy to strip away atmospheres over millions of years. The planets in this system orbit so close that a year lasts only a few Earth days. They are trapped in the blast zone of a stellar furnace. But not all hope is lost. The outer planets, designated E, F, G, and H, sit farther from the star. They may have held onto their atmospheres. Webb is still watching, still searching. 15 additional observations are scheduled for TRAPPIST-1e alone. Early hints suggest this world might have a nitrogen-rich atmosphere with traces of methane, similar to Titan, the frozen moon of Saturn. But the data is not yet conclusive. The star's violent outbursts contaminate the readings, making it difficult to separate planetary signals from stellar noise. We are pushing the limits of what any telescope can do. And while we struggle to find signs of life on distant worlds, Webb has uncovered something far more troubling about the early universe: black holes that should not exist. The universe is 13.8 billion years old. In its earliest moments, there was nothing but hot plasma and radiation. No stars, no galaxies, no structure of any kind. Just a seething ocean of particles expanding outward from the Big Bang. Then gravity began its slow work. Matter clumped together. The first stars ignited. Galaxies started to form. And at the hearts of those galaxies, black holes grew. Slowly, steadily, feeding on gas and dust over billions of years until they became the supermassive monsters we observe today. At least, that is what the models predicted. Webb has shattered those predictions. In November of 2025, astronomers announced the discovery of a supermassive black hole in a galaxy called CANUCSLRDZ 8.6. The name is technical, but what it represents is staggering. This galaxy existed just 570 million years after the Big Bang. The universe was barely 4% of its current age, a cosmic infant. And yet, at the center of this infant galaxy, a black hole was already devouring matter at a rate that defies explanation. It was growing far faster than any model allows, far faster than physics says is possible. This is confirmed, peer-reviewed, published in Nature Communications. The black hole's mass compared to its host galaxy breaks every rule we thought we understood. In the modern universe, supermassive black holes typically contain about 1/100% of their galaxy's stellar mass. For every 10,000 units of mass in stars, there is roughly 1 unit of mass in the central black hole. This ancient monster, its mass is 10% of the galaxy's total, 1,000 times higher than the expected ratio. The research team described it simply: the black hole is growing faster than the galaxy that hosts it. But this is not an isolated case. Webb has found hundreds of similar objects scattered across the early universe. Scientists call them little red dots because of their small size and reddish color in infrared images. Many of them appear to contain rapidly growing black holes surrounded by hot gas and dust. 70% of the little red dots examined so far show signs of active black hole feeding. Gas swirling at speeds exceeding 2 million miles per hour. Temperatures hot enough to ionize atoms. Energy output that rivals entire galaxies. These objects challenge everything we thought we knew about cosmic evolution. Either black holes in the early universe were born much larger than we assumed, collapsing directly from massive clouds of primordial gas, or they found ways to feed at rates that should be physically impossible. Or our models of the early universe are fundamentally wrong. The standard model of cosmology has guided science for decades. It has passed every test thrown at it, until now. Something happened in those first few 100 million years that we do not understand. Something that allowed monsters to grow in the darkness, before the first light had fully dawned. And those monsters were not alone. Webb found something else lurking in the ancient cosmos. Galaxies that appeared too big, too bright, and too soon. When Webb first opened its eyes to the distant universe, astronomers expected to find small, dim, primitive galaxies. The early cosmos should have been a nursery of infant structures, tiny clumps of stars just beginning to form, building blocks that would eventually merge into the grand spirals and ellipticals we see today. Instead, they found giants, galaxies containing tens of billions of stars, fully formed, blazing with light, existing just 500 million years after the Big Bang. Some of them rivaled the mass of our own Milky Way, which took over 13 billion years to reach its current size. The headlines were immediate. Universe breakers, they called them. Objects so massive, so early, that they seemed to violate the fundamental laws of cosmic evolution. Scientists scrambled for explanations. The Standard Model of Cosmology describes how the universe evolved from the Big Bang to the present day. It explains how matter clumped together under gravity, how dark matter formed invisible scaffolding for galaxies to grow upon, and how long these processes should take. According to this model, galaxies in the early universe should have been small. There simply was not enough time for them to grow large, yet there they were, massive and defiant. Some researchers suggested the model itself might be broken. Perhaps dark matter behaved differently in the early universe. Perhaps the fundamental constants of physics had changed over time. The implications were enormous. Decades of established science hung in the balance, but then came a twist. Further analysis revealed that many of these impossibly massive galaxies were not what they seemed. They were bright, yes, but their brightness came not from stars alone. Hidden at their centers were actively feeding black holes. Gas spiraling into these black holes generated enormous amounts of heat and light, making the galaxies appear far more massive than they actually were. When scientists removed these black hole-powered objects from their calculations, the crisis softened. The remaining galaxies were still larger than expected, but not impossibly so. The Standard Model survived, battered but intact, confirmed by a study published in 2024. The universe is not broken, but a mystery remains. Even after accounting for the black hole contamination, Webb still sees roughly twice as many massive early galaxies as the models predict. Something about the early universe allowed stars to form faster than they do today. Perhaps the denser conditions made it harder for stellar winds to blow gas away. Perhaps the raw materials for star formation were more abundant. Perhaps galaxies were simply better at converting gas into stars. In early 2025, Webb delivered another surprise. A massive spiral galaxy nicknamed the Big Wheel, existing less than 2 billion years after the Big Bang. Spiral structures like this require stability. They require time to settle into graceful rotating arms. Yet there it was, elegant and ancient, spinning in defiance of expectation. The early universe was not the chaotic mess we imagined. It was organized, structured, mature, and somewhere in that ancient darkness, frozen worlds were being born. Worlds without stars, worlds without light, wandering alone through the void. Trillions of them. Imagine a planet drifting through space with no star to orbit, no warmth from above, no sunrise, no sunset, just endless darkness stretching in every direction. A frozen world tumbling through the void, untethered to anything. These are rogue planets, and the James Webb Space Telescope has revealed they are everywhere. In 2023, Webb discovered 42 pairs of these wandering giants in the Orion Nebula. Scientists called them Jupiter Mass Binary Objects, or JUMBOs, pairs of gas giants orbiting each other instead of a star, drifting together through interstellar space like cosmic dance partners with no stage beneath them. No one expected to find so many, and no one could explain how they formed. Then, in 2024, Webb went deeper. Astronomers pointed the telescope at a young star-forming region called NGC 1333, about 1,000 light-years from Earth. They found 6 more rogue planets, including the lightest ever detected, a world just 5 times the mass of Jupiter, surrounded by a disk of dust and gas. That disk changes everything. Dust disks are where planets form. Around normal stars, these disks condense into rocky worlds and gas giants over millions of years. But this rogue planet has its own disk. It could be forming its own miniature planetary system, moons, or perhaps something stranger, tiny worlds orbiting a frozen giant that itself orbits nothing. The discovery suggests that rogue planets do not just form around stars and get ejected. Some of them condense directly from clouds of gas, the same way stars do. They are failed stars, objects that gathered enough mass to collapse but not enough to ignite nuclear fusion, and their numbers are staggering. Theoretical studies suggest rogue planets may outnumber the stars in our galaxy. 2 trillion, perhaps more. For every point of light you see in the night sky, there could be multiple dark worlds drifting between them, invisible, silent, cold. In 2025, astronomers detected one of these wanderers about 10,000 light-years away. They found it not by seeing it directly, but by watching it bend the light of a distant star. Gravitational lensing. The rogue planet's mass warped space-time itself, acting like a cosmic magnifying glass. This world has about 70 times the mass of Earth, smaller than Saturn, larger than Neptune, and it drifts alone, unbound to any stellar system, confirmed through simultaneous observations from Earth and the Gaia Space Telescope. But the strangest discovery came in 2025, when Webb and the Very Large Telescope observed a rogue planet called CHA 1107. This frozen giant is eating, devouring gas and dust at a rate of 6 billion tons per second, accretion bursts that mirror the feeding behavior of young stars. A planet acting like a star, growing, changing, evolving in the darkness. We do not fully understand what these objects are, or what they might become, and while orphan worlds drift through the galaxy in silence, Webb has been watching something far more violent, stars preparing to die. For decades, astronomers have faced a puzzle. When massive stars die, they explode as supernovae. The most common type of massive star is the red supergiant, bloated, aging giants that have exhausted the fuel in their cores. Theory says these stars should dominate the supernova population, but when scientists look at the records, red supergiants seem to rarely explode. Where were they hiding? On June 29, 2025, a supernova appeared in a galaxy 40 million light-years away. Astronomers named it SN 2025 PHT, and when they traced back through archived images, they made a discovery that solved a mystery stretching back generations. Webb had already photographed this galaxy in 2024. Hubble had observed it as far back as 1994. By comparing the images, scientists could identify the exact star that exploded. It was a red supergiant, confirmed. But here is why it had been invisible for so long. The star was wrapped in a cocoon of dust so thick that it blocked almost all visible light. In optical wavelengths, it appeared more than 100 times dimmer than it should have. Hubble could not see it at all. Only Webb's infrared vision could pierce the veil and reveal the dying giant within. The star shone 100,000 times brighter than our own star, but the dust hid nearly all of that light from view. This is the dustiest, reddest supergiant progenitor ever observed before explosion. It answers the question that plagued astronomers for years. The massive stars are exploding. They are just shrouded in cloaks of cosmic dust, invisible to telescopes that see only visible light. The lead researcher put it clearly: "We have been arguing that dust might be hiding these stars. Even we did not expect to see something this extreme." Webb caught the star in its final moments. The images show a bloated, unstable giant on the edge of collapse. And then, the core gave way. Gravity won. The outer layers blasted outward at thousands of miles per second, leaving behind either a neutron star or a black hole. Hubble captured the aftermath in July of 2025, a brilliant point of light where the hidden star once lurked. This discovery has enormous implications. If the most massive stars in the universe are hiding behind dust, then our census of stellar death has been incomplete. The supernova rate might be higher than we thought. The production of heavy elements, forged in stellar explosions and scattered across the cosmos, might be more prolific than we calculated. And there is one more unsettling detail. The closest red supergiant to Earth is Betelgeuse, a massive, unstable star in the constellation Orion, visible to the naked eye on winter nights. Betelgeuse has been dimming and brightening erratically. Some scientists believe it may explode within the next 100,000 years, perhaps sooner. When it does, it will be visible in daylight, a second star in our sky. But before we witnessed death, Webb revealed something even stranger, a planet that should not exist, shaped like a lemon, with an atmosphere no one can explain. 1 million miles. That is all that separates a bizarre world from the dead star it orbits. For comparison, Earth sits 93 million miles from its own star. This planet clings to its host at roughly 1% of that distance. A year on this world lasts less than 8 hours, and the gravity is so intense that the entire planet has been stretched into the shape of a lemon. Scientists call it PSR J2322-2650b, but the technical name hardly matters. What matters is that this world defies every theory of planetary formation we possess. The host star is a pulsar, a neutron star, the collapsed core of a massive star that died in a supernova explosion long ago. Neutron stars are among the densest objects in the universe. A teaspoon of neutron star material would weigh billions of tons, and this one spins rapidly, completing thousands of rotations every second, sweeping beams of radiation across space like a cosmic lighthouse. But here is what baffles scientists. The pulsar emits mostly gamma rays and high-energy particles, invisible to Webb's infrared detectors. This means the telescope could observe the planet without being blinded by starlight, a perfect view, unobstructed. What Webb saw made researchers pause. The planet's atmosphere is dominated by helium and carbon. No hydrogen, no water vapor, no familiar gases. Instead, the skies are filled with soot-like carbon clouds. And deep inside, under crushing pressures, that carbon may be crystallizing into diamonds. The lead scientist described it bluntly. This is a new type of planet atmosphere that nobody has ever seen before. Confirmed. Published in the Astrophysical Journal Letters in December of 2025. The mystery deepens when you consider how this world formed. Normal planets coalesce from disks of gas and dust around young stars. But this planet orbits a stellar corpse. Did it survive the supernova that created the pulsar? Did it form afterward from debris? Did it wander in from somewhere else and get captured? None of the standard explanations fit. One theory suggests the planet is actually the stripped remnant of a companion star. Pulsars sometimes have partners. Over billions of years, the pulsar can steal material from its companion, whittling it down to a fraction of its original mass. Perhaps this lemon-shaped world is what remains of a star that lost 99.9% of itself. But even that does not fully explain the carbon atmosphere. Nuclear physics does not produce pure carbon in the quantities observed. The researchers admit they may be looking at an entirely new class of object, something between a planet and a stellar remnant, something without a name. "We did not expect this," one scientist said. "It is extremely different from anything we predicted." And somewhere across the cosmos, Webb found another impossible world, a broiling hell planet covered in magma oceans, wrapped in an atmosphere that should have been stripped away long ago. The rules keep breaking. 280 light-years from Earth, a planet orbits so close to its star that a single year lasts only 11 hours. The world is called TOI 561b, and its surface is an ocean of molten rock. Temperatures exceed 3,000 degrees. Lava churns beneath a hazy sky. By every known principle, this planet should be a bare, airless rock. It is not. In December of 2025, Webb detected something extraordinary, an atmosphere, thick enough to redistribute heat from the day side to the night side, substantial enough to register in the telescope's infrared instruments. This should be impossible. Planets this close to their stars are bombarded by radiation. Stellar winds and ultraviolet light should have stripped away any atmosphere within a few million years. Yet TOI 561b still has one. After more than 10 billion years of existence, the planet is ancient, one of the oldest rocky worlds ever discovered. It formed when the universe was less than half its current age, and somehow, despite all that time baking under the glare of its star, it held onto a blanket of gas. Researchers call it a lava ball wrapped in air, confirmed by 37 hours of continuous observation with Webb's near-infrared spectrograph. The measurements showed a dayside temperature far cooler than expected for a bare rock. If the planet had no atmosphere, it should have reached nearly 5,000 degrees. Instead, Webb recorded about 3,000 degrees. The only explanation is that gases are absorbing and redistributing heat. But what kind of atmosphere survives under such conditions? Scientists believe the answer lies in the magma itself. Molten rock releases gases. Volatile compounds bubble up from the interior and escape into the sky. On Earth, volcanic eruptions do the same thing, but on a much smaller scale. On this hell world, the entire surface is a volcanic ocean. The atmosphere is being constantly replenished from below. The planet essentially breathes through its lava. This discovery has profound implications for the search for life. Astronomers have long assumed that planets too close to their stars cannot maintain atmospheres. They are considered dead zones, unworthy of study. But if a world can replenish its atmosphere through geological activity, then the habitable zone might be wider than we thought. Not that TOI 561b is habitable. Far from it. Nothing could survive on a world where the ground itself is liquid fire. But the principle applies elsewhere. Rocky planets with active interiors might be able to cling to their atmospheres in environments we once dismissed as hostile. The rules are shifting, and they shifted again when Webb turned its instruments toward distant black holes, not just feeding, not just growing, but colliding, merging, sending ripples through the fabric of spacetime itself. The earliest black hole merger ever detected was waiting in the ancient darkness, 740 million years after the Big Bang. The universe is still young, galaxies are still forming, and two supermassive black holes are spiraling toward each other, locked in a gravitational death dance that will shake the very structure of spacetime. Webb caught them in the act. The discovery, announced in 2024, represents the most distant black hole merger ever observed. Two galaxies crashing together, two monsters at their cores, circling closer and closer, destined to become one. This is confirmed, published, verified through spectroscopic analysis that separated the light signatures of each black hole. One of the black holes contains 50 million times the mass of our star. The other is likely similar in size, though buried so deep in gas and dust that precise measurements are difficult. Together, they will eventually merge into a single supermassive black hole with the combined mass of 100 million stars. The collision will release gravitational waves, ripples in spacetime that propagate outward at the speed of light. These waves are too low in frequency for current detectors like LIGO to sense. But future observatories, including the space-based LISA mission, approved by the European Space Agency, will be able to detect mergers like this one. The lead researcher explained the significance. Our findings suggest that merging is an important route through which black holes can rapidly grow, even at cosmic dawn. But the implications stretch further. The two galaxies involved in this merger are small, comparable in stellar mass to the Large Magellanic Cloud, a dwarf galaxy that orbits our own Milky Way. Yet each one harbors a supermassive black hole larger than the one at the center of our galaxy. This ratio is wrong. By modern standards, black holes should be much smaller compared to their host galaxies. But in the early universe, the balance was different. Black holes dominated, they grew first, and galaxies struggled to catch up. Together with other Webb findings, our results show that massive black holes have been shaping the evolution of galaxies from the very beginning. The merger also reveals something about the violence of the early cosmos. Galaxies did not form in isolation. They collided, they merged, they tore each other apart and rebuilt from the wreckage. The supermassive black holes at their centers were active participants in this chaos, not passive bystanders. When the two black holes in this system finally merge, they will release more energy in gravitational waves than all the stars in both galaxies combined. A silent explosion rippling through the universe at the speed of light. We cannot see gravitational waves directly. We can only infer them from their effects. But Webb gave us the before picture. The two black holes, still separate, still spiraling. And while black holes collide in the distant past, Webb discovered something unsettling about the galaxies that formed around them. They were messy, turbulent, struggling to survive. The Milky Way is a graceful spiral. Stars orbit the galactic center in orderly paths, tracing elegant arms that sweep across 100,000 light-years of space. It took billions of years for our galaxy to settle into this structure. Billions of years for the chaos of formation to calm into the cosmic pinwheel we see today. Webb looked back to a time before that calm existed. In 2025, astronomers used the telescope to study galaxies that existed between 4 and 600 million years after the Big Bang. They expected to find young systems, still organizing themselves. What they found was worse. The galaxies were messy, turbulent, violent. Gas clouds were not rotating smoothly. Instead, they churned with chaotic motions, slamming into each other at speeds that disrupted any attempt at structure. Stars formed in bursts, not steady streams. The gravitational forces within these galaxies were pulling in every direction at once. One researcher described it simply: these early galaxies struggled to settle. The observations were captured using a technique called grism spectroscopy, which allowed Webb to measure the motion of gas within individual galaxies. The data revealed velocity dispersions far higher than seen in modern galaxies. Gas was moving erratically, driven by supernovae explosions, black hole activity, and gravitational interactions with neighboring systems. This is the most detailed look yet at how galaxies formed, confirmed, published in the monthly notices of the Royal Astronomical Society. The findings explain something that had puzzled astronomers. Early galaxies often appear clumpy and irregular in Webb images, bright knots of star formation scattered across their surfaces, with no clear pattern. Now we understand why. The gas from which those stars formed was itself disordered. Turbulence prevented the smooth, rotating structures that would come later. But there is a deeper implication. If galaxies in the early universe were this chaotic, then the environments for planet formation were equally hostile. Stars born in violent bursts may have scattered their planetary disks before worlds could fully form. Black holes feeding aggressively may have sterilized entire regions with radiation. The places where life could have arisen were rare, and yet some galaxies did manage to organize earlier than expected. The spiral galaxy, nicknamed the Big Wheel, discovered in early 2025, shows elegant rotating structure despite existing less than 2 billion years after the Big Bang. Somehow, this galaxy avoided the worst of the chaos, or perhaps it found a way to calm itself faster than its neighbors. The early universe was not uniform. Some regions were violent, others were stable, and in those stable pockets, the conditions for complexity could emerge. Webb is helping us map which regions were which. But stability was not the only requirement for complexity. Planets also needed protection, and Webb revealed that around the most common stars in the galaxy, that protection may be impossible to maintain. Red dwarfs are everywhere. They make up roughly 70% of all stars in the Milky Way. Small, dim, and long-lived, they burn their fuel so slowly that they can shine for trillions of years. If life needs time to evolve, red dwarfs offer more time than any other type of star. But there is a problem. Red dwarfs are violent. They unleash flares of radiation with frightening regularity, bursts of ultraviolet light, and charged particles that dwarf anything our own star produces. These flares are not occasional events. They happen constantly, especially in young red dwarfs, and the planets that orbit these stars sit dangerously close to the blast zone. Because red dwarfs are dim, their habitable zones are narrow and close. A planet needs to orbit within a few million miles to receive enough warmth for liquid water. At that distance, stellar flares become existential threats. Webb's observations of the TRAPPIST-1 system revealed this danger in stark detail. The 7 planets orbiting TRAPPIST-1 are bathed in radiation. The star is known to be volatile, releasing flares that have been recorded by multiple observatories over the years. These flares do not just warm the planets, they strip atmospheres away, molecule by molecule, over millions of years. The inner planets have already lost any protection they might have had. TRAPPIST-1b and c show no signs of substantial atmospheres. TRAPPIST-1d, once considered a prime candidate for habitability, appears similarly barren. The outer planets may have fared better simply because they sit farther from the worst of the radiation, but distance alone is not enough. Even TRAPPIST-1e, the most promising world in the system, faces an uncertain future. Researchers studying the planet found that the star's activity contaminates their atmospheric readings. Flares emit light at specific wavelengths that can mimic the signatures of planetary gases. Separating the star's signal from the planet's signal is extraordinarily difficult. 15 additional observations have been scheduled to account for this interference. Scientists will observe TRAPPIST-1e alongside the inner planet TRAPPIST-1b, which is believed to be a bare rock. By comparing the two, they can subtract the star's contribution and isolate any atmosphere on the outer world. If TRAPPIST-1e has no atmosphere, the implications extend far beyond this one system. Red dwarfs are the most common stars in the galaxy. If planets around these stars cannot retain atmospheres, then the vast majority of potentially habitable worlds may be dead zones. The search for life would narrow dramatically. But Webb has not given up. The telescope continues to observe red dwarf systems, searching for exceptions, searching for worlds that somehow survived the bombardment, searching for atmospheres that refuse to die. And while some planets cling to their air against impossible odds, others are forming in ways no one predicted, directly imaged. Inside a ring of debris, captured by Webb in a cosmic first. For decades, astronomers discovered planets indirectly. They watched stars wobble under the gravitational tug of unseen companions. They measured tiny dips in brightness when planets crossed in front of their stars. They inferred the existence of worlds they could not actually see. Webb changed that. In June of 2025, the telescope accomplished something never done before. It directly imaged a newly forming planet inside the debris disk of a young star. The star is called TWA7, located about 111 light-years from Earth. It is young by cosmic standards, only 6.4 million years old, still surrounded by rings of gas and dust left over from its formation. These rings are where planets are supposed to form, and now, for the first time, we have seen one in the act. The planet sits in a gap between the first and second ring of the debris disk. Its mass is roughly 1/3 that of Jupiter. It orbits 52 times farther from its star than Earth does from ours. A cold, distant world still gathering material from the surrounding dust. This is confirmed. Published in Nature. The odds of this being a background galaxy masquerading as a planet were calculated at less than 1%. The discovery is remarkable for several reasons. First, it validates a method of planet hunting that has been theorized for years. Gaps in debris disks have long been suspected to harbor planets. The gravity of a forming world clears out a lane in the surrounding material, like a snowplow pushing through fresh powder. TWA-7's disk has 3 distinct rings, suggesting multiple planets may be present. Webb found one. Others may follow. Second, it provides a snapshot of planetary formation in progress. We are not looking at a finished world. We are watching the construction. The planet is still embedded in the disk that birthed it, still potentially accreting material, still evolving. Third, it demonstrates Webb's extraordinary precision. Directly imaging a planet requires blocking out the overwhelming glare of its parent star. The contrast between star and planet is immense. Webb's coronagraphs and image processing techniques made it possible to isolate this faint point of light from the stellar noise. The research team had specifically targeted young stars that could be viewed pole-on, essentially looking down into the system from above. This orientation provides a clear view of the disk structure and any planets within it. TWA-7 is not the last. Other young systems are already queued for observation. The technique is proven. The hunt continues. And there is something poetic about this discovery. We are watching a planet form around a star that is itself a baby by cosmic standards. Creation unfolding in real time, the universe building new worlds even as we observe. But formation is only half the story. Webb also captured something at the opposite end of existence. The farthest supernova ever seen, a star dying at the edge of the observable universe. 730 million years after the Big Bang, the universe is emerging from its dark ages. The first stars have ignited. The first galaxies are beginning to glow. And somewhere in that primordial light, a massive star collapses. The explosion releases more energy in seconds than our star will produce in its entire 10 billion year lifetime. A gamma-ray burst screams outward at nearly the speed of light. Behind it, the expanding shell of the supernova carries heavy elements forged in the dying star's core. Iron, nickel, cobalt, the building blocks of rocky worlds scattered into the void. 13 billion years later, Webb caught the afterglow. On March 14, 2025, a space telescope called SVOM detected a brilliant flash of gamma rays. Follow-up observations with the Very Large Telescope confirmed the distance. The light had traveled from an era when the universe was just 5% of its current age. Then Webb pointed its infrared eye at the source. Roughly 110 days after the initial burst, the telescope captured images that separated the fading supernova from its host galaxy. The explosion was still visible, still glowing, even after billions of years of travel across the expanding cosmos. This is the most distant supernova ever confirmed, published in Astronomy and Astrophysics in December of 2025. The discovery matters because it connects two phenomena that scientists have long believed are related. Gamma-ray bursts are among the most energetic events in the universe. They have been observed for decades, but their exact origins remained debated. The leading theory was that long-duration gamma-ray bursts are produced by collapsing massive stars, supernovae. Webb provided the smoking gun. The supernova emerged at exactly the same location as the gamma-ray burst. Same coordinates, same host galaxy, same event. The massive star that created the burst also exploded as a supernova. Theory confirmed. But there is more. The host galaxy is small and faint, one of countless dwarf galaxies that populated the early universe. Inside that tiny system, a single massive star lived and died, seeding its surroundings with heavy elements that would eventually form new stars, new planets, perhaps even life. We are connected to events like this one. Every atom of iron in your blood, every speck of calcium in your bones, was forged in a stellar explosion billions of years ago. The supernova Webb observed is part of that lineage, a distant ancestor in the cosmic family tree. And the telescope is still watching, still searching the ancient light for more explosions, more gamma-ray bursts, more evidence of the violent processes that shaped the universe we inhabit today. But the early universe held one more secret, something even older than the first supernovae, the echoes of the very first generation of stars, stars that may never have been seen directly until now. Before the first galaxies formed, before the first supernovae scattered heavy elements into space, there was a generation of stars that has never been seen. Scientists call them population 3 stars. These were the firstborn, colossal giants forged from pure hydrogen and helium, the only elements that existed in the aftermath of the Big Bang. No carbon, no oxygen, no metals of any kind, just the simplest atoms in the universe, collapsing under gravity until fusion ignited in their cores. Population 3 stars were massive beyond anything that exists today, hundreds of times heavier than our own star. They burned hot and bright, consuming their fuel in just a few million years. Then they exploded, seeding the cosmos with the first heavy elements. Every atom heavier than helium that exists today traces its origin to these primordial giants. But no one has ever seen one directly. They died too long ago. Their light has been stretched and dimmed by 13 billion years of cosmic expansion. Webb may have found their fingerprints. In 2024, astronomers studying the galaxy GNZ11 discovered something unexpected in its outer halo. A cloud of gas with no heavy elements at all, pure hydrogen and helium, pristine material unchanged since the Big Bang. This cloud could be the birthplace of population 3 stars, the raw material from which the first generation would have formed. The discovery is not confirmation. Scientists are careful to note that they have not directly observed a population 3 star, but the presence of pristine gas in the vicinity of an ancient galaxy is exactly what theory predicts. The ingredients are there, the conditions are right. GNZ11 is one of the most distant galaxies ever observed, existing just 430 million years after the Big Bang. At its center sits a supermassive black hole devouring matter at a ferocious rate. But on its outskirts, untouched pockets of primordial material still linger. This is the closest we have come to witnessing the dawn of stellar creation. The significance extends beyond curiosity. Population 3 stars are believed to have produced the first black holes through direct collapse. They may have triggered the formation of the first galaxies by ionizing surrounding gas. They were the engines that transformed the universe from a dark, featureless void into the structured cosmos we see today. If Webb can find more pristine gas clouds, scientists can study the conditions under which the first stars formed. They can test models of primordial nucleosynthesis. They can trace the chemical evolution of the universe from its simplest state to the complexity of the present day. The ghosts of the first light are still out there, hidden in the faintest signals from the most distant reaches of space. And Webb is listening. But while the telescope peers into the ancient past, it has also revealed something troubling about the present. The universe is expanding, and it is expanding faster than it should. The universe is getting bigger. Every galaxy is drifting away from every other galaxy. Space itself is stretching, carrying everything along for the ride. This has been known for nearly a century. Edwin Hubble first measured the expansion in the 1920s. Since then, astronomers have refined the measurement countless times, pinning down what is called the Hubble constant, a number that describes how fast the universe expands per unit of distance. The problem is that the numbers do not agree. When scientists measure the expansion using nearby stars and galaxies, they get one value, roughly 73 kilometers per second per megaparsec. But when they calculate the expansion using the cosmic microwave background, the faint radiation left over from the Big Bang, they get a different value, roughly 67 kilometers per second per megaparsec. The difference is small in absolute terms, but it is far too large to be explained by measurement error. Something is wrong, either with the measurements or with our understanding of the universe itself. This discrepancy is called the Hubble tension, and it has haunted cosmology for over a decade. Webb was supposed to help resolve it. In December of 2024, researchers published the largest study of cosmic distances ever conducted with Webb. They used 3 different methods to measure distances to galaxies that hosted supernovae. They cross-checked everything. They combined data from multiple independent teams. The result was clear. The Hubble Space Telescope's measurements were accurate. The discrepancy was not caused by calibration errors or instrument problems. Webb confirmed what Hubble had been saying all along. The universe is expanding faster than the Standard Model predicts. Confirmed, published in the Astrophysical Journal. This leaves 2 possibilities. Either there is some new physics that accelerates expansion in ways we do not yet understand, or the standard model of cosmology, which has guided science for decades, is incomplete. Dark energy is already part of the model, the mysterious force that drives galaxies apart faster and faster over time. But dark energy alone does not explain the Hubble tension. Something else is at play. Some theorists suggest that dark energy might change over time, behaving differently in the early universe than it does today. Others propose new particles or forces that operated in the first few 100,000 years after the Big Bang. The possibilities are vast and unsettling. The discrepancy suggests that our understanding of the universe may be incomplete. Those were the words of Adam Rees, the Nobel laureate who led the study. He won his prize for discovering that the expansion of the universe is accelerating. Now he is confronting evidence that even that discovery may not tell the whole story. Webb has not solved the Hubble tension. It has made it worse. The mystery has deepened, and mysteries seem to follow this telescope everywhere it looks, including toward a red giant star that may soon give us the show of a lifetime. Look up on a clear winter night and find the constellation Orion. The hunter stands tall in the southern sky, his belt of 3 stars unmistakable. But look closer. At his shoulder, glowing with a distinct reddish hue, is a star that has captured human imagination for centuries, Betelgeuse. It is one of the largest stars visible to the naked eye, a red supergiant so massive that if placed at the center of our solar system, its surface would extend past the orbit of Jupiter, perhaps past the orbit of Saturn. The star is bloated, unstable, and nearing the end of its life. Betelgeuse will explode as a supernova. This is certain. The only question is when. In late 2019 and early 2020, the star dimmed dramatically. For weeks, it faded to less than half its normal brightness. Headlines erupted. Was Betelgeuse about to blow? Were we about to witness the death of a nearby star in real time? The answer turned out to be no. The dimming was caused by a cloud of dust ejected from the star's surface, temporarily blocking its light. Betelgeuse was not dying, it was coughing. But the episode revealed how unstable the star has become. Webb and other observatories have continued to monitor Betelgeuse, tracking its temperature, its brightness, and the structure of its outer layers. The data shows a star in turmoil. Surface temperatures fluctuate. Material is being ejected into space. The star pulsates, swelling and contracting over periods of months. Some researchers believe Webb has detected signs of accelerating instability, changes in the infrared signature that suggest the core may be approaching collapse. But predictions are difficult. Astronomically speaking, imminent could mean tomorrow or 100,000 years from now. What we know is this: when Betelgeuse finally explodes, it will be spectacular. The supernova will outshine the full moon. It will be visible during the day, a brilliant point of light hanging in the blue sky. For weeks, perhaps months, humanity will watch a star die 650 light-years away. But we are safe. The distance is too great for the explosion to harm Earth. No deadly radiation will reach us. No shockwave will disrupt our atmosphere. We will simply witness one of the most powerful events in the universe from a front row seat. The heavy elements forged in that explosion will eventually drift through space, mixing with clouds of gas and dust, seeding future generations of stars and planets. Some of those elements may one day become part of new worlds, new life. We are stardust, watching stardust prepare to scatter. And when it happens, Webb will be watching too, recording the death of a giant in unprecedented detail, adding one more chapter to the story of how stars live and die. But the story does not end with death. It continues with creation. And Webb has found places where creation is happening right now. On worlds that orbit nothing at all, a planet without a star should be a dead end. A frozen ball of gas drifting through the void, unable to form anything, unable to evolve, just a cosmic orphan waiting out eternity in the cold darkness between the stars. Webb proved that assumption wrong. In July of 2025, astronomers published findings that challenge everything we thought we knew about planetary formation. Using Webb's sensitive infrared instruments, they studied 8 rogue planets with masses between 5 and 10 times that of Jupiter. These wandering giants float freely through space, unbound to any stellar system. 6 of them showed something remarkable: extended infrared emissions surrounding each world, the unmistakable signature of warm dust. These rogue planets have debris disks, the same kind of structures that surround young stars, the same swirling rings of gas and dust from which planets form. Except here, the central object is not a star, it is a planet. Even more striking, Webb detected silicate grains within these disks. Silicates are minerals, the building blocks of rocky worlds. Their presence indicates that dust is clumping together, crystallizing, taking the first steps toward forming solid objects. These massive planets may be nurseries for miniature planetary systems, confirmed, published in the Astronomical Journal. The implications are staggering. Planetary formation is not exclusive to stars. Lonely, starless worlds drifting through the galaxy can build their own companions. Moons, perhaps, or something stranger. Tiny rocky bodies orbiting frozen giants that themselves orbit nothing. The lead researcher put it clearly: the formation of planetary systems is not exclusive to stars, but might also work around lonely, starless worlds. This discovery forces us to expand our definition of what a planetary system can be. We have always imagined planets orbiting stars. Now we must imagine planets orbiting planets, systems within systems, structures nested inside structures, all the way down. And there may be trillions of these objects in our galaxy alone. Rogue planets are difficult to detect because they emit almost no light. They do not reflect the glow of a parent star. They do not transit across a stellar disk. They are invisible against the blackness of space unless you know exactly where to look and have instruments sensitive enough to catch their faint infrared heat. Webb can see them, and Webb is finding them everywhere. The 6 rogue planets with debris disks were discovered in a young star-forming region about 1,000 light-years from Earth, but similar objects likely exist throughout the galaxy, in the spaces between stars, in the halos of galaxies, in the vast emptiness that separates one stellar neighborhood from another. We have barely begun to map this hidden population. And if rogue planets can form moons, what else might they harbor? Could liquid water exist beneath the icy surfaces of their companions, warmed by tidal forces and radioactive decay? Could chemistry proceed in those dark oceans, sheltered from the harsh radiation of space? The questions multiply faster than the answers. But Webb found something even closer to home. A cold giant lurking in our stellar backyard, captured in unprecedented detail. 12 light-years from Earth, a failed star drifts through the darkness. It is called Epsilon Indi Ab, and until recently, it was little more than a gravitational whisper, a tug on its parent star that hinted at something massive hiding nearby. Webb turned that whisper into a portrait. In 2024, astronomers used the telescope to directly image this object, confirming its existence and revealing its properties in unprecedented detail. Epsilon Indi Ab is a gas giant roughly 6 times the mass of Jupiter. It orbits its star at a distance comparable to Saturn's orbit around our own star, and it is one of the coldest exoplanets ever directly observed. Surface temperatures hover around 200 degrees below 0 Fahrenheit, cold enough to freeze methane, cold enough to condense exotic ices that do not exist on any world in our solar system. This is confirmed. The planet is real, visible, studied. What makes this discovery significant is not just the planet itself, but what it represents for the future of exoplanet science. Most exoplanets are detected indirectly. We see the wobble they induce in their stars, or the dimming they cause when they pass in front of stellar disks. But direct imaging captures actual light from the planet itself. Photons that traveled from that distant world to Webb's mirrors, a real picture of an alien atmosphere. Epsilon Indi Ab is close enough and cold enough that Webb could study its composition. The data suggests an atmosphere rich in methane and possibly ammonia, similar in some ways to Jupiter and Saturn, but colder, older, more evolved. The planet has been cooling for billions of years, slowly radiating away the heat of its formation into the emptiness of space. And here is where it gets interesting. Epsilon Indi Ab orbits a star that is itself remarkable. Epsilon Indi A is a K-type star, slightly smaller and cooler than our own star. It is part of a triple system that includes 2 brown dwarfs, failed stars, that never ignited fusion in their cores. The planetary architecture of this system is complex. Multiple objects of varying masses, all bound together by gravity, all influencing each other's orbits over billions of years. By studying Epsilon Indi Ab, scientists can learn about planetary evolution in ways that observations of our own solar system cannot provide. Jupiter and Saturn are roughly 4.5 billion years old. Epsilon Indi Ab may be even older. It represents a more advanced stage of giant planet aging. What happens to atmospheres over such timescales? How do clouds form and dissipate? How does internal heat escape through layers of exotic gas? Webb is beginning to answer these questions, and the answers will inform our understanding of giant planets everywhere, including those that might harbor moons with liquid water. Moons where life could theoretically arise, even around cold, ancient worlds far from the warmth of any star. But warmth is not always necessary. As Webb revealed, sometimes heat comes from unexpected places. When we think of habitable worlds, we picture Earth, a rocky planet bathed in starlight, warmed by a yellow star, wrapped in a protective atmosphere. But Webb has revealed that habitability might take forms we never imagined. Deep inside frozen worlds, heat can persist for billions of years. The source is not starlight. It is not proximity to a stellar furnace. It is something far more subtle. Radioactive decay, the slow breakdown of unstable atoms buried in a planet's core, releasing energy particle by particle, warming the interior from within. And tidal forces, the gravitational stretching and squeezing that occurs when a moon orbits close to a massive planet. The constant flexing generates friction. Friction generates heat. Enough heat, in some cases, to maintain liquid water beneath shells of ice. This is not theory. We see it in our own solar system. Europa, a moon of Jupiter, has a global ocean beneath its frozen crust. Enceladus, a moon of Saturn, shoots geysers of water vapor into space. Both worlds are heated not by starlight, but by internal processes. Both are considered among the most promising places to search for life beyond Earth. Webb has observed these moons, measuring their surfaces, studying their compositions, searching for signs of geological activity. And what the telescope found suggests that the conditions for subsurface oceans are not rare. They may be common throughout the galaxy. Rogue planets with large moons could harbor similar environments, frozen on the surface, but warm and wet beneath, cut off from starlight, but sustained by the slow burn of radioactive elements and the relentless pull of gravity. Life in such places would be alien in ways we can barely imagine. No photosynthesis, no connection to stellar energy cycles, just chemistry proceeding in darkness, powered by the planet's own internal heat. Scientists call this chemosynthesis. On Earth, it occurs in the deepest ocean trenches, where hydrothermal vents spew mineral-rich water into the abyss. Entire ecosystems thrive there, independent of light. Tube worms, blind shrimp, bacteria that metabolize sulfur instead of oxygen. If such life can exist on Earth, it can exist elsewhere. Webb cannot detect life directly. No telescope can, but it can identify the conditions that make life possible: liquid water, chemical energy sources, stable environments over geological timescales. The telescope has found these conditions in places we never expected: around rogue planets, inside debris disks, on frozen moons orbiting distant giants. The search for life is no longer confined to the habitable zones of stars. It has expanded to include the dark spaces between them, the frozen wanderers, the hidden oceans. The universe is larger and stranger than we ever imagined, and Webb is just getting started. But not all of its discoveries inspire wonder. Some inspire unease, like the realization that the cosmic neighborhood we thought we understood is full of objects we have only begun to catalogue. We have mapped the stars. We have catalogued the galaxies. We have traced the structure of the cosmic web across billions of light years. But there is a population of objects that has largely escaped our surveys. Brown dwarfs. These are failed stars. Objects that formed from collapsing clouds of gas, just like stars do, but never gathered enough mass to ignite hydrogen fusion in their cores. They glow faintly with residual heat from their formation, then slowly fade into darkness over billions of years. Webb has revealed that brown dwarfs are far more numerous than we realized, and they are far more diverse. In December of 2025, the telescope captured images of a young star cluster called Westerlund 2, located about 20,000 light-years from Earth. Hidden among the brilliant young stars, Webb found a population of brown dwarfs with masses as low as 10 times that of Jupiter. These are among the lightest free-floating objects ever detected using the process of stellar formation. They blur the line between planets and stars, too large to have formed in a planetary disk, too small to sustain fusion. Something in between. Confirmed. The cluster contains approximately 3,000 stars and an unknown number of these transitional objects. The discovery challenges our categories. What do we call an object that forms like a star but has the mass of a planet? Is it a failed star or a successful planet? The distinction matters because it affects how we count objects in the galaxy, how we estimate the total mass of matter, how we model the evolution of stellar populations. And brown dwarfs are not the only hidden population. Webb has found objects even smaller, rogue planets with masses just a few times that of Jupiter, drifting through star-forming regions without any stellar companion. Objects that may have been ejected from planetary systems or that collapsed directly from gas clouds before they could grow larger. The galaxy is crowded with these invisible wanderers. Traditional surveys using visible light miss most of them. Brown dwarfs are too cool and too faint. Rogue planets are even harder to detect. Only infrared telescopes like Webb can spot their dim thermal signatures against the cold background of space. And the implications are significant. Dark matter is the invisible scaffolding that holds galaxies together. Its nature remains one of the greatest mysteries in physics. Some researchers have speculated that brown dwarfs and rogue planets might account for a portion of this missing mass. The numbers do not quite work. Brown dwarfs and rogue planets together cannot explain all of dark matter, but they contribute, and we did not know how much until Webb began counting them. The invisible census is underway. Every observation adds new entries, new objects that were always there, lurking in the darkness, waiting to be found. But some of Webb's discoveries are not just surprising, they are sobering. Reminders that the universe operates on scales and timelines that dwarf human comprehension. Carbon is everywhere in the universe. It forms in the cores of dying stars and scatters across space in supernova explosions. It is the backbone of organic chemistry, the foundation of life as we know it. And under the right conditions, it transforms into something extraordinary: diamonds. Webb has found evidence that diamond formation may be happening inside alien worlds, not as rare gemstones buried in rock, but as entire layers of crystallized carbon deep within planetary interiors. The lemon-shaped planet orbiting a pulsar, discovered in 2025, offers the clearest example. Its atmosphere is dominated by carbon. Soot-like clouds drift through its helium-rich skies. And beneath that atmosphere, pressures build to levels that would crush any material on Earth. Under such pressures, carbon does not remain as soot. It crystallizes. Atoms lock into the rigid lattice structure of diamond, layer upon layer, building up over billions of years. Scientists cannot see inside this planet directly, but they can model what happens when carbon-rich atmospheres overlay dense interiors. The physics is well understood. At sufficient pressure and temperature, diamond formation is inevitable. The planet may have a diamond core. This is not confirmed in the sense of direct observation, but it is consistent with everything Webb measured: the atmospheric composition, the extreme pressures implied by the planet's proximity to its pulsar host, the spectral signatures of carbon in various forms. And this planet is not unique. Theoretical models suggest that diamond-rich interiors could exist in many worlds throughout the galaxy. Gas giants with enough carbon in their atmospheres, super-Earths with extreme internal pressures, rogue planets that formed from carbon-rich material in the first place. The implications extend beyond geology. Diamonds conduct heat efficiently. A diamond-rich layer inside a planet would affect how heat flows from core to surface. It would influence volcanic activity, atmospheric evolution, and potentially the conditions for habitability on any moons orbiting such a world. We are only beginning to understand the exotic chemistry that governs alien planets. Webb has revealed that the universe is not composed of the familiar materials we see on Earth. It is filled with extremes, pressures that compress atoms into new configurations, temperatures that melt rock and vaporize metal, environments where the ordinary becomes extraordinary. Carbon is just one example. Other elements may behave in equally surprising ways under alien conditions. Metallic hydrogen in the cores of gas giants, superionic water ice in the mantles of ice giants, exotic alloys formed under pressures we cannot replicate in any laboratory. Webb is a window into these extreme environments. It cannot visit these worlds. It cannot drill into their cores, but it can measure their atmospheres, infer their compositions, and model what lies beneath. And what lies beneath is stranger than we ever imagined. But strangeness is not the only theme of Webb's discoveries. There is also beauty and tragedy, and the slow, inevitable march of cosmic time. 13 billion years ago, a galaxy died, not in a spectacular explosion, not in a collision with another system. It simply stopped forming stars. The raw material for new stellar birth was exhausted or expelled. The galaxy went quiet. Its existing stars continued to burn, but no new ones were born to replace them. Webb found this cosmic corpse in 2024, a dead galaxy from an era when the universe itself was barely 700 million years old, the youngest galactic graveyard ever discovered. This should not have happened so quickly. Galaxies form stars continuously over billions of years. The Milky Way still produces new stars today, roughly 4.5 billion years after it formed. Star formation is the heartbeat of a galaxy. When it stops, the galaxy is, in a cosmic sense, dead. But this ancient galaxy had already flatlined when the universe was a mere 5% of its current age. Researchers call these objects quiescent galaxies. They are not rare in the modern universe. Elliptical galaxies, for example, often show little ongoing star formation, but finding one so early challenges our models of galactic evolution. Something shut down star formation with brutal efficiency. The most likely culprit is the supermassive black hole at the galaxy's center. As black holes feed, they release enormous amounts of energy. Jets of radiation and superheated gas blast outward, heating and expelling the cold gas that would otherwise collapse into new stars. This process is called feedback, and it can sterilize a galaxy in remarkably short time. Webb's observations support this interpretation. The dead galaxy shows signs of having hosted an active black hole in its past. The black hole may have consumed so much material so quickly that it destroyed the very conditions needed for continued star formation. The galaxy choked on its own appetite. Confirmed. Published in Nature in 2024, the discovery reveals something profound about the relationship between black holes and their host galaxies. They do not simply coexist. They shape each other. Black holes can nurture galaxies by stirring up gas and triggering star formation, or they can murder them by blowing that gas away. The balance between creation and destruction plays out across cosmic history. Some galaxies thrive, others die young. Webb is cataloging these outcomes, counting the living and the dead, mapping the cosmic graveyard that stretches across billions of light years. And in doing so, it is teaching us about the fate of our own galaxy. The Milky Way has a supermassive black hole at its center. Relatively quiet now, but it has fed before, and it will feed again. 4 billion years from now, our galaxy will collide with Andromeda. The merger will send gas spiraling toward both central black holes. What happens next is uncertain. Creation or destruction? The answer may already be written in the light from the ancient dead. The Andromeda galaxy is falling toward us, 2.5 million light-years away and closing. In roughly 4 billion years, it will collide with the Milky Way. The two spirals will merge, their stars scattering into new orbits, their central black holes eventually combining into a single supermassive monster. This is not speculation. It is confirmed by decades of observations. The motion of Andromeda, relative to our galaxy, has been measured with extraordinary precision. The collision is inevitable, but Webb has shown us what such collisions look like in real time. Across the distant universe, the telescope has captured galaxies in various stages of merger. Spirals distorted into chaotic shapes, streams of stars torn from their parent systems, bursts of star formation triggered by the compression of gas clouds, and at the centers, black holes drawing closer, preparing for their own union. These images are previews of our future. The merger will not destroy Earth. Stars are separated by such vast distances that direct collisions are extraordinarily rare. Our planet will likely survive the event, flung into some new orbit around the merged galactic core. The night sky will change, the familiar constellations will dissolve, but the world itself will endure. What Webb has revealed, however, is that mergers are not gentle. The gravitational chaos triggers waves of star formation. Gas clouds collapse under the stress of tidal forces. Supernovae rates spike as massive, short-lived stars are born and die in rapid succession. Radiation bathes entire regions of space, and the central black holes do not merge quietly. As they spiral together, they emit gravitational waves that ripple through space-time. The final coalescence releases more energy than all the stars in both galaxies combined, a silent thunderclap echoing across the universe. Future gravitational wave detectors will be able to sense mergers like the one that awaits us. But that technology lies decades or centuries in the future. For now, we can only observe the aftermath of distant collisions and imagine what our descendants will witness. Webb has also shown that galactic mergers seed the cosmos with heavy elements. The star formation triggered by collisions produces massive stars that live fast and die young. Their supernovae scatter iron, gold, uranium, and all the other elements heavier than hydrogen and helium. The collision with Andromeda will enrich the merged galaxy with new material. Future generations of stars will form from this enriched gas. Future planets will incorporate these elements into their crusts and cores. In a very real sense, the collision will be an act of creation, destruction and rebirth intertwined. Webb cannot see the future, but it can show us the past. And in the past, it has found countless examples of galaxies transforming through merger, evolving, changing. The universe is not static. It is a machine of constant renewal, and our place within it is smaller than we ever imagined. 40 light-years is nothing in cosmic terms, a rounding error on the scale of the galaxy, a short walk compared to the vastness between stars. Yet within that tiny radius, Webb has found 7 Earth-sized planets around a single star, worlds that once seemed like promising candidates for life, worlds that have now been largely ruled out. TRAPPIST-1b, scorched and airless. TRAPPIST-1c, same story. TRAPPIST-1d, no Earth-like atmosphere detected. The outer planets remain under investigation, but the pattern is troubling. The closest potentially habitable worlds we know of are being eliminated one by one. And this is just one system. The nearest star system, Alpha Centauri, may harbor a giant planet, but giants are not hospitable to life as we know it. Any moons they might possess remain purely hypothetical. The nearest confirmed exoplanet, orbiting a single star like our own, is Barnard's star B, roughly 6 light-years away. Its mass and orbit suggest a frozen world, far outside the habitable zone. Webb has found thousands of exoplanets across the galaxy, but the ones close enough to study in detail are proving hostile, and the ones that might be habitable are too far away for current technology to examine thoroughly. The silence is deafening. We have searched for signals from other civilizations for over 60 years. Radio telescopes have scanned the skies for artificial transmissions. Optical surveys have looked for laser pulses. Nothing. Not a single confirmed detection of intelligent life. Some researchers argue that the search has barely begun. The galaxy is vast. Our instruments are limited. We have sampled only a tiny fraction of the possibilities. Others suggest that the silence has a darker explanation. Perhaps intelligent life is rare. Perhaps it tends to destroy itself before it can spread across the stars. Perhaps the conditions for complex biology are so specific that Earth is an anomaly. Webb cannot answer these questions directly. It is not designed to search for life, but every world it studies adds data to the equation. Every atmosphere it analyzes either supports or undermines the hypothesis that habitable conditions are common. So far, the data is mixed. Rocky planets exist in abundance. That is confirmed. But rocky planets with stable atmospheres in habitable zones around quiet stars appear to be rare. The universe is full of worlds, but most of them are dead. This does not mean we are alone. It means the search is harder than we hoped, and it means that if life does exist elsewhere, it may be separated from us by distances we cannot cross, by timescales we cannot comprehend, by gulfs of empty space that make communication impossible. We are very small, and the universe is very large, but we are still looking, still hoping, still pointing our telescopes at the darkness and waiting for an answer. The James Webb Space Telescope has been operational for just over 3 years. In that time, it has rewritten textbooks, shattered assumptions, and revealed a universe stranger and more complex than we ever imagined. Black holes that grew too fast, galaxies that formed too early, planets that should not exist, atmospheres that defy explanation, rogue worlds building their own systems in the darkness between stars. And through it all, a single thread connects every discovery. We are smaller than we thought. The universe does not revolve around Earth. It does not care about human timescales or human concerns. It operates on principles that stretch across billions of years, across distances so vast that light itself struggles to cross them. Webb has shown us our cosmic neighborhood in unprecedented detail. Alpha Centauri, just 4 light-years away, may harbor a giant planet we never knew existed. Asteroids pass through our orbital space, and we barely have time to track them. The stars we see at night are violent, unstable, surrounded by radiation that would sterilize any world too close. But Webb has also shown us beauty. Nebulae glowing with the light of newborn stars, galaxies spiraling through the void in elegant formation, planets forming inside rings of dust, following the same processes that built our own world 4.5 billion years ago. Creation and destruction, life and death, the same cycles repeating across the cosmos, on scales that humble the imagination. And somewhere in that vastness, we exist. A small rocky planet orbiting an ordinary star in an unremarkable spiral galaxy. One world among trillions. One species among however many might exist, scattered across the observable universe. Webb cannot tell us if we are alone, but it can tell us what we are looking for. Atmospheres with the right chemistry, planets in the right orbits, stars stable enough to permit life to arise. The search continues. Every observation adds another piece to the puzzle. Every discovery refines our understanding of what is possible and what is not. The universe is not hostile, it is indifferent. And in that indifference, there is room for hope. Life arose here. It could arise elsewhere. The conditions exist. The ingredients are scattered across every galaxy Webb has observed. Whether intelligence ever joins us in the silence remains unknown. But we are no longer guessing in the dark. We are looking, measuring, learning. The James Webb Space Telescope is not just a machine. It is a mirror, reflecting back to us our own smallness and our own potential, showing us where we came from and hinting at where we might go. The journey has only begun. And if you made it this far, you are part of it. Every question asked, every wonder sparked, every moment spent looking up at the night sky connects you to the same drive that built this telescope and pointed it at the stars. We are the universe becoming aware of itself, and Webb is helping us see. Black holes are supposed to stay put, anchored at the centers of galaxies by the combined gravity of billions of stars. They sit like cosmic drains, pulling matter inward, growing slowly over eons. They do not move, they do not flee, except when they do. In late 2025, Webb confirmed something that had been suspected for years: a supermassive black hole hurtling through space at over 2 million miles per hour, not drifting, not wobbling, running. The object was first spotted by the Hubble Space Telescope as a strange streak of light trailing from a distant galaxy. Researchers initially thought it might be a cosmic ray hit on the detector, an artifact, a glitch. But the streak persisted in follow-up observations. And when Webb turned its infrared eyes toward the source, the truth emerged. A supermassive black hole had been ejected from its home galaxy, kicked out by gravitational forces so violent that they overcame the pull of hundreds of billions of stars. The mechanism is called a three-body interaction. When galaxies merge, their central black holes eventually spiral toward each other. If a third black hole enters the system, the gravitational dynamics become chaotic. One of the three can be flung outward at tremendous speed, while the other two merge. This is what happened here, confirmed by spectroscopic analysis that matched the velocity of the runaway to predictions from computer simulations. But the streak of light trailing behind the black hole is not just debris, it is stars, new stars, forming in the wake of the monster as it plows through intergalactic gas. The black hole compresses the gas as it passes. The compression triggers collapse. Stars ignite in a trail stretching over 200,000 light-years. A cosmic contrail marking the path of destruction and creation. Nothing like this has ever been observed before. The implications are unsettling. If supermassive black holes can be ejected from galaxies, then the universe contains wandering monsters we have never accounted for. Invisible predators drifting through the voids between stellar systems. Black holes with no galaxies to call home, no stable orbits, no predictable paths. How many are out there? We do not know. Detecting a runaway black hole requires catching it in the act of interacting with surrounding material. If it passes through empty space, it leaves no trace. The one Webb found was discovered by accident, a lucky alignment, a chance observation. There could be thousands more, millions, silent and dark, threading through the cosmic web at speeds that boggle the mind. And here is the uncomfortable thought. Our own galaxy will merge with Andromeda in 4 billion years. Both galaxies contain supermassive black holes. If the merger goes poorly, one of those black holes could be ejected, including ours. The neighborhood is more dangerous than we assumed, but danger is not always distant. Sometimes it lurks in familiar places, like the giant planet in our own cosmic backyard, where Webb discovered weather systems that mirror the strangest storms on Earth. Saturn's largest moon is one of the strangest worlds in our solar system. Titan has a thick atmosphere, denser than Earth's. It has lakes and seas, rivers and rain, but the liquid is not water. It is methane, hydrocarbon oceans lapping against frozen shorelines under an orange, hazy sky. Webb has been watching Titan, and what it found changes our understanding of this bizarre world. In 2024, the telescope captured evidence of cloud convection in Titan's northern hemisphere for the first time. Methane clouds forming, rising, and producing storms that drop hydrocarbon rain onto the surface below. This is weather, alien weather, but weather nonetheless. The same basic processes that drive thunderstorms on Earth, operating on a moon where temperatures hover around -290 degrees Fahrenheit. The discovery was made by combining Webb observations with data from the Keck telescope in Hawaii. Together, they tracked cloud formations moving across Titan's disk, evolving over hours, behaving exactly as meteorological models predicted. Confirmed. Published by an international team studying Titan's atmospheric dynamics. But here is what makes this significant. Titan's northern hemisphere is where most of the moon's lakes and seas are located. The methane cycle on Titan mirrors the water cycle on Earth. Liquid evaporates from the surface, rises into the atmosphere, condenses into clouds, and falls as rain. The rain feeds rivers that carve channels into the frozen landscape and drain into hydrocarbon seas. Webb observed this cycle in action for the first time from Earth orbit. The implications extend beyond Titan itself. If complex weather systems can operate on a frozen moon nearly 1 billion miles from Earth, then similar processes might occur on countless worlds throughout the galaxy. Exomoons orbiting giant planets in distant systems, rogue planets with thick atmospheres and internal heat sources. Any world with the right combination of temperature, pressure, and volatile compounds. Weather is not unique to Earth. It is a universal phenomenon, playing out in different chemical languages across the cosmos. And Titan offers something else. A laboratory for studying prebiotic chemistry. The hydrocarbon compounds raining from Titan's skies are the same building blocks that may have led to life on early Earth. Methane, ethane, and more complex organic molecules accumulating in lakes where chemical reactions can proceed over billions of years. No one is claiming that Titan hosts life. The temperatures are far too cold for liquid water, and without liquid water, biology as we know it cannot function. But the chemistry is there. The raw materials are abundant. The processes are ongoing. Webb will continue to monitor Titan as seasons change on that distant moon. A single Titan year lasts 29 Earth years. The northern summer is just beginning. The storms may intensify, the rains may grow heavier, and we will be watching. But Titan is not the only familiar world where Webb found surprises. Closer still, the largest planet in our solar system was putting on a show unlike anything recorded before. Jupiter is a world of superlatives. the largest planet in our solar system, the fastest rotation, completing a full day in just 10 hours, the strongest magnetic field of any planet, 20,000 times more powerful than Earth's, and the most violent auroras ever observed. Webb pointed its instruments at Jupiter in 2024 and captured something extraordinary. The auroras at the planet's poles were not just glowing, they were erupting, fizzing and popping with activity that changed from minute to minute. Auroras on Earth are caused by charged particles from the stellar wind interacting with our magnetic field. They shimmer and dance, but slowly, predictably. Jupiter's auroras operate on a completely different scale. The charged particles slamming into Jupiter's atmosphere carry far more energy. They come not just from the stellar wind, but from the volcanic moon Io, which spews sulfur and other materials into space at a rate of 1 ton per second. This material gets caught in Jupiter's magnetic field, accelerated to tremendous speeds, and funneled toward the poles. The result is an auroral display that makes Earth's northern lights look like a candle flame compared to a forest fire. Webb's infrared vision captured details invisible to other telescopes: temperature variations in the auroral zones, chemical signatures of molecules being torn apart and reassembled by the bombardment of particles. The three-dimensional structure of the magnetic field lines channeling energy into the atmosphere. The data revealed something unexpected. The auroras were changing faster than models predicted. Bright spots appeared and vanished in seconds. Entire regions flared and dimmed as if the planet's magnetic field were hiccuping. Researchers are still analyzing what this means. One possibility is that the interaction between Jupiter and Io is more dynamic than previously understood. Another is that processes deep within Jupiter's atmosphere affect how auroral energy is distributed. Either way, the observations demonstrate that even worlds we have studied for centuries can still surprise us. And Webb found something else at Jupiter. Above the famous Great Red Spot, a storm that has raged for at least 300 years, the telescope detected atmospheric features never seen before. Layers of haze and unusual chemical compositions that suggest the storm extends far higher into the atmosphere than ground-based telescopes could resolve. Jupiter is not a static world. It is evolving, changing. Its storms shift and merge. Its auroras pulse with rhythms we are only beginning to understand. Webb will continue to observe the giant planet, building a time-lapse record of its atmospheric behavior. Over years and decades, patterns may emerge. The physics governing this enormous world may finally come into focus. But Jupiter is at least familiar. Webb has also found objects far stranger. Visitors from beyond our solar system, passing through on journeys that span the galaxy. Chapter 29, 449 words. Chapter 30, Visitors from the Void. In late 2024, astronomers discovered something that should not be in our solar system. A comet, yes, but not one of ours. It came from interstellar space. The object was designated 3I/Atlas, making it only the third confirmed interstellar visitor ever detected. The first was Oumuamua in 2017, a cigar-shaped object that sparked wild speculation before vanishing into the outer solar system. The second was Comet Borisov in 2019, a more conventional-looking comet that confirmed interstellar objects were not unique. 3I/Atlas arrived in 2024 and immediately drew the attention of every major observatory on Earth, including Webb. The telescope observed the comet in August of 2025 as it made its closest approach. What it found was remarkable. The comet behaves like a comet. It has a coma, a fuzzy envelope of gas and dust surrounding its nucleus. It has jets, streams of material shooting from its surface as ices vaporize in the warmth of our stellar neighborhood. It even has a tail, albeit a faint one, trailing behind as it races through the inner solar system. But its composition is alien. Spectroscopic analysis revealed chemical signatures different from comets that formed in our solar system. The ratios of certain elements and compounds suggest this object coalesced around a distant star billions of years ago, in a planetary system with different conditions than our own. We are looking at a piece of another solar system, a fragment of a world that never was, ejected into the void and wandering for eons before chance brought it to our doorstep. Confirmed. Webb's observations were combined with data from the Hubble Space Telescope and ground-based observatories to build a comprehensive portrait of the visitor. The comet is leaving now, falling back out into interstellar space, never to return. In a few years, it will be too faint for even the most powerful telescopes to detect. It will continue its journey through the galaxy, perhaps passing close to other stars, perhaps drifting in darkness forever. But its brief visit taught us something important. Interstellar objects are not rare. They pass through our solar system regularly. We simply lacked the instruments to detect them until recently. How many have come before? How many passed by unnoticed while humanity was still learning to make fire? The galaxy is full of debris, scattered remnants of planetary formation, wandering between the stars. Some of that debris may carry complex organic molecules, the building blocks of life, drifting on cosmic currents, seeding new worlds wherever they land. Webb cannot track every interstellar visitor, but it can study the ones we find, and each one tells a story about a distant solar system we will never visit. The universe is connected in ways we are only beginning to understand. Galaxies do not float in isolation. They are connected by vast filaments of gas and dark matter, stretching across hundreds of millions of light years. This structure is called the cosmic web, and Webb is revealing it in unprecedented detail. Imagine the universe as a sponge. Galaxies cluster along the surfaces of the sponge, concentrated in filaments and nodes. Between them lie enormous voids, regions of nearly empty space where few galaxies exist. This structure formed in the first few 100 million years after the Big Bang. Tiny variations in the density of matter were amplified by gravity over cosmic time. Dense regions pulled in more material and became denser still. Sparse regions emptied out as their matter drained toward the filaments. Webb has imaged portions of this cosmic web directly. In 2024, the telescope captured light from distant quasars, the brilliant cores of active galaxies powered by feeding black holes. As this light traveled toward us, it passed through the intergalactic medium. The gas between galaxies absorbed certain wavelengths, leaving fingerprints in the quasar spectra. By analyzing these fingerprints, astronomers mapped the distribution of gas along the line of sight. They found filaments of hydrogen stretching between galaxies, exactly where the cosmic web predicted they should be. Confirmed. The invisible scaffolding of the universe made visible for the first time at these distances. But Webb found something unexpected. Some filaments contained more gas than models predicted, others contained less. The distribution was clumpy, uneven, more complex than the smooth structures suggested by simulations. This matters because the cosmic web controls how galaxies grow. Gas flows along filaments, feeding into galaxies at the nodes. If the filaments are uneven, then galaxy growth is uneven. Some systems receive abundant fuel for star formation, others starve. The observations are forcing theorists to revise their models. The universe is messier than we assumed, more chaotic, less predictable. And the cosmic web is not static, it evolves over time. Filaments merge, voids expand, galaxies migrate along gravitational currents, drawn toward the densest concentrations of matter. Our own Milky Way sits at a relatively modest node in the cosmic web. The local filament connects us to the Virgo cluster, a collection of over 1,000 galaxies about 50 million light-years away. We are falling toward Virgo, pulled by its gravity, part of a flow that has been ongoing for billions of years. Webb cannot observe the local cosmic web directly. We are embedded within it, but by studying distant structures, we can infer what our own neighborhood looks like from the outside. A small strand in an infinite tapestry, a single thread in a web that spans the observable universe. And somewhere in that web, hidden in the darkness between the filaments, is the substance that holds everything together, the mystery that refuses to be solved, dark matter. 85% of all matter in the universe is invisible. It does not emit light. It does not absorb light. It does not interact with ordinary matter except through gravity. We cannot see it, touch it, or detect it directly with any instrument ever built. Yet without it, galaxies would fly apart. Stars would never form. The cosmic web would not exist. Everything we observe depends on something we cannot observe, dark matter. Webb was not designed to study dark matter directly. No telescope can. But it can observe the effects of dark matter with precision never before achieved. And those observations are deepening the mystery rather than solving it. Gravitational lensing is the key technique. When light from a distant galaxy passes near a massive object, it bends. The massive object acts like a lens, distorting and magnifying the background light. The amount of bending reveals the total mass of the lens, including both visible matter and dark matter. Webb has observed dozens of gravitational lensing systems. In each case, the dark matter halo surrounding the lensing galaxy is far more massive than the visible stars and gas. The ratio is consistent with cosmological predictions, about 6 times more dark matter than ordinary matter, confirmed across multiple observations. The dark matter is there, but what is it? The leading hypothesis for decades has been that dark matter consists of undiscovered particles, weakly interacting massive particles, or WIMPs, that formed in the early universe and have been drifting through space ever since. Experiments on Earth have searched for these particles for over 30 years. Nothing has been found. Other hypotheses exist. Axions, hypothetical particles even lighter and more elusive than WIMPs, primordial black holes, formed in the first moments after the Big Bang, modified gravity theories that eliminate the need for dark matter entirely by changing the laws of physics. Webb's observations cannot distinguish between these possibilities directly, but they can constrain the options. If dark matter behaves in certain ways, it should leave detectable signatures in the distribution of galaxies and the structure of gravitational lenses. So far, the data is frustratingly consistent with the simplest models. Cold, dark matter, moving slowly, clumping under gravity, forming halos around galaxies exactly as predicted. The mystery endures. Whatever dark matter is, it shaped the universe we inhabit. It determined where galaxies formed. It controlled the flow of gas along the cosmic web. It created the gravitational wells where stars ignited and planets coalesced. We exist because of something we cannot see, and every observation Webb makes adds another constraint, another data point, another piece of a puzzle that may take decades more to solve. The universe keeps its secrets well, but Webb has found places where new secrets are being written, where stars are being born and planetary systems are taking shape. The nurseries of creation. Stars are not born alone. They emerge from vast clouds of gas and dust, molecular nurseries spanning dozens of light years. Within these clouds, gravity pulls material together, forming dense cores that collapse and heat until fusion ignites. Webb has peered into these nurseries with clarity no telescope has achieved before. The Carina Nebula, the Eagle Nebula, the Orion Nebula, iconic regions of star formation that have been photographed for decades. But previous images showed only the surfaces of these clouds, the outer layers illuminated by nearby stars. Webb sees through them. Infrared light passes through dust that blocks visible wavelengths. For the first time, we can observe the interiors of star-forming regions, the dense cores where protostars are gathering mass, the jets of material shooting from young stellar objects, the disks of gas and dust where planets are beginning to form. In 2022, Webb released its first images of the Carina Nebula. The detail was staggering. Pillars of gas, sculpted by radiation from hot young stars. Hundreds of previously unseen protostars embedded in the cloud. evidence of star formation proceeding in waves, triggered by the expansion of earlier stellar generations. But the observations have continued, and they have revealed something surprising. Star formation is more efficient than we thought. Models predicted that only a small percentage of a molecular cloud's mass would convert into stars. The rest would be blown away by stellar winds and radiation before it could collapse. But Webb's observations show higher conversion rates in some regions, more stars forming, more mass being used. The early universe may have operated the same way. If star formation was more efficient in the past, it would explain why Webb sees so many massive galaxies at high redshift. The raw material was converted into stars faster than modern theories assumed, confirmed by surveys of multiple star-forming regions. The physics of stellar birth is being rewritten, and within those birth clouds, Webb has found something else. The earliest stages of planetary system formation, protoplanetary disks, surround many young stars, rings of gas and dust that will eventually coalesce into planets, moons, asteroids, and comets. Webb has imaged these disks in unprecedented detail, revealing gaps where planets may already be forming, spiral arms driven by gravitational instabilities, and chemical gradients that determine what kinds of worlds can emerge. One disk, surrounding a star just a few 100,000 years old, showed evidence of water ice at distances where rocky planets might form, the building blocks of habitable worlds, present from the earliest stages of stellar evolution. Creation is happening right now. Across the galaxy, new solar systems are taking shape. Some may one day host life, and we are watching it happen in real time. But not all stellar systems are simple. Some are far more complex and far more dangerous. Most stars in the galaxy are not alone. They have companions. Binary systems, where two stars orbit each other, are more common than single stars like ours. Triple systems exist. Quadruple systems exist. The stellar population is social. This creates problems for planets. In a binary system, gravitational forces are complex. A planet must find a stable orbit, either close to one star or far enough out to orbit both. The wrong orbit leads to chaos. Gravitational tugs from both stars can stretch orbits, increase eccentricity, and eventually fling planets into the void or send them crashing into their parent stars. Webb has discovered planets surviving in these hostile environments, and their existence challenges our models. The potential planet around Alpha Centauri A is one example. Alpha Centauri is a binary system with two stars orbiting each other every 80 years. The candidate planet orbits one of those stars at a distance where it should experience significant gravitational perturbations from the companion, yet it appears to have survived for billions of years. Other binary systems show similar surprises. Webb has imaged debris disks around binary stars, indicating that planetary formation is possible even in gravitationally complex environments. Some of these disks show gaps where planets may already exist. And in 2025, astronomers announced the discovery of a planet orbiting a star in a system with not two but three stellar components. A hierarchical triple, where a close binary is orbited by a distant third star. The planet orbits the distant star, far enough from the inner binary to maintain stability. Confirmed. Published in peer-reviewed journals, planets can form and survive in systems we once considered too chaotic. The implications extend to habitability. Binary and multiple star systems were often dismissed as poor candidates for life. The gravitational chaos, the variable radiation environments, the unstable orbits all seem to preclude the kind of long-term stability life requires. But if planets can survive in these systems, then the number of potentially habitable worlds in the galaxy increases dramatically. Binary stars are everywhere. If even a fraction of them host stable planets, the census of possible homes for life expands by billions. Webb cannot determine habitability directly, but it can identify where planets exist, what their orbits look like, and whether conditions might permit liquid water. Each discovery adds to the catalogue, and the catalogue is growing faster than anyone predicted. Single stars, binary stars, pulsars, brown dwarfs, rogue planets. The diversity of environments where worlds can form is staggering. The universe is more creative than our theories imagined. But creativity has limits. Some environments are simply too extreme for anything familiar, and Webb has found worlds that push those limits to the breaking point. There is a planet where it rains glass. Sideways. HD 189733. B orbits so close to its star that one side is permanently locked, facing the inferno. Temperatures on the day side exceed 2,000 degrees. Silicate rock vaporizes, rises into the atmosphere, and is carried by supersonic winds to the night side, where it condenses and falls as molten glass. Webb has studied this world, measured its temperature variations, mapped the transition zones between eternal day and eternal night. It is a hell beyond imagination, and it is not unique. The category of exoplanets known as hot Jupiters has revealed extreme after extreme. Gas giants orbiting so close to their stars that they complete a year in less than 2 Earth days. Worlds where iron vaporizes on the day side and rains down on the night side. Atmospheres with temperature inversions, where upper layers are hotter than lower layers, defying the behavior of every planet in our solar system. Webb's spectroscopic capabilities have opened a window into these alien atmospheres. Water vapor, carbon dioxide, methane, sulfur dioxide, the chemical fingerprints of distant skies, read across light years of space. And the chemistry is strange. Some hot Jupiters show evidence of clouds made from corundum, the mineral that forms rubies and sapphires. Others have atmospheres dominated by titanium oxide, a compound used in sunscreen on Earth. The combinations are exotic, the conditions extreme, the environments utterly unlike anything in our experience. Yet these worlds exist, confirmed by transit observations, radial velocity measurements, and now direct spectroscopy from Webb. And they raise a question. If the universe can produce worlds this strange, what else might be out there? Rocky planets with surfaces of pure diamond, compressed from carbon-rich mantles under extreme pressure, ocean worlds covered entirely by water hundreds of miles deep, with no solid surface at all. Carbon planets where graphite and carbides replace the silicate rocks familiar on Earth. Webb has found hints of some of these exotic compositions. A super-Earth with an atmosphere suggesting a magma ocean surface. A Neptune-like world with an unusual carbon-to-oxygen ratio. The data is fragmentary, but the implications are vast. We assumed planets would look like the worlds in our solar system, perhaps with minor variations. Rocky planets like Earth and Mars, gas giants like Jupiter and Saturn, ice giants like Uranus and Neptune. The universe had other ideas. Every observation reveals new possibilities, new combinations of mass, composition, and orbit, new environments that challenge our definitions of what a planet can be. Webb is expanding our vocabulary, teaching us new words for worlds we never imagined. And in that expanded vocabulary, somewhere, there may be a word for a world like Earth, a world where life could arise. The search continues. In 1990, the Voyager 1 spacecraft turned its camera back toward Earth from a distance of nearly 4 billion miles. The image it captured showed our planet as a tiny speck, a fraction of a pixel, suspended in a beam of scattered light. Carl Sagan called it the pale blue dot. He wrote that everyone we have ever known, every civilization that has ever risen and fallen, existed on that mote of dust. Webb has not imaged Earth. It cannot. The telescope points away from our region of space to avoid damage from the brightness of nearby objects. But it has done something perhaps more profound. It has shown us what Earth would look like from the outside. By studying exoplanets in distant systems, Webb has revealed what signatures a living world might produce. Oxygen in the atmosphere, methane that should not persist without biological replenishment, water vapor and carbon dioxide in the right proportions, the chemical fingerprints of life. Earth has all of these signatures. If an alien civilization pointed a telescope like Webb at our solar system, they could detect our presence. They would see a rocky planet in the habitable zone of a stable star, wrapped in an atmosphere that screams of biological activity. We are detectable, visible, a data point in someone else's survey. This realization changes the search for life. It means the techniques we are developing to find biosignatures on exoplanets could be used by others to find us. The universe may already know we are here, or it may not. The distances are vast. The signals are faint. Even Webb, the most powerful space telescope ever built, can only study the atmospheres of a handful of nearby worlds in detail. An equivalent telescope in another galaxy would see nothing of Earth at all. We are visible but small, detectable but obscure, one world among trillions. Webb has placed Earth in context, not as the center of the universe, but as one example of what is possible, a template for habitability that may or may not be replicated elsewhere. The search for other Earths continues. Webb has identified candidates, rocky planets in habitable zones with the right sizes and orbits. But confirming that any of them hosts life will require technology beyond what currently exists. Future telescopes may achieve what Webb cannot: direct imaging of exoplanet surfaces, spectroscopic analysis sensitive enough to detect trace biosignatures, missions to nearby systems that could study alien worlds up close. The journey will take decades, perhaps centuries, but it has begun, and every discovery Webb makes adds to our understanding of where life might arise, where it might thrive, and where we fit in the cosmic story. We are the pale blue dot, small and fragile, but we are also the species that built this telescope and pointed it at the stars. That is not nothing.